Welcome to The Machine, a computer science education podcast from Waterford Institute of Technology. My name is Rob O'Connor and we're following on with our series discussing sub-disciplines of computing. We've covered a number of them so far, and today we are going to talk about automotive computing. This is tied up with a stream we have on our Bachelor of Science in Applied Computing programme. That's automotive and automation. On the panel with me today, we have Brendan Jackman, who is a lecturer in the department and the leader of the automotive stream and also the automotive research group. I may have pronounced that incorrectly. Did I get the name right there, Brendan?
It's the automotive control group.
Apologies. There you go. It shows you I've done my research very, very well. And we also have a graduate of the programme, somebody who used to haunt the halls of WIT, used to be a purveyor of memes across the college, and set up the WIT Meme Society or Facebook page. I remember back in the day. He's now based in Cambridge, where he works as a connected vehicle R&D engineer. David Evans. David, thanks for joining us on the podcast today.
Hi, thank you very much for having me.
No bother at all. It's nice to see you.
Yeah, likewise.
Look, flattery will get you everywhere. Okay, as always, housekeeping. If you want to get in touch with the show, ask machine_podcast on Twitter, or you can look us up on the WIT website and you'll get all their details there. If you like what you hear, please leave us a nice review. And if you don't like what you hear, well, keep your mouth shut. Okay, so we'll start off by talking about automotive computing. If I'm in my head, as somebody who knows very little about automotive computing, the first thing I would think of is CarPlay, because I plug my phone into the car and I get this screen in front of me and I can listen to podcasts and, you know, internet radio and music and all that kind of stuff. But it's not really about that, is it, Brendan? It's about a lot more.
Well, it is about that nowadays, but if we go back to basics, if you go back to, say, the 1980s, 1990s, when electronics first became introduced into cars, one of the very first systems was, for example, fuel injection and ignition control. And that kind of brought some transistorized electronics into cars, which allowed you to time the engine performance to get the best performance from the engine and more fuel efficiency and so on. And that was kind of like the breakthrough in terms of automating some of the engine functions. So when the microprocessor came along and things became a little bit more kind of widespread in that area, then more and more applications became introduced into the car. So then we had things like ABS braking, then we had things like power steering and so on. And over the decades, the number of functions in a car, the number of functions controlled by electronics and ultimately software, basically mushroomed. And then as each new generation came along, everybody wanted more and more features. So there's a couple of basic principles driving the amount of software in cars. The two main ones would be safety, obviously. Okay, so we want to make cars safer. We want to reduce fatalities and deaths on the road. There's lots of EU initiatives to drive down the number of fatalities and accidents on the roads. Most notably the work done by the RSA, the Road Safety Authority in Ireland, who have won awards for their efforts in road safety promotion in Ireland. So we're actually quite good in the European league table in terms of safety on the roads here. But anyway, safety is one big issue that's driving the amount of software. So if you think about all the kind of gadgets you have in your car now, things like emergency brake assist and lane keep assist and all these features that sort of help you drive the car. And the ultimate kind of manifestation of that would be the autonomous vehicle, where the car ultimately drives itself. So you can think of something like the Tesla car, where there is a sort of an automated driving feature in there. It's not quite autopilot as they market it, and they've been pulled up on that in countries like Germany, because a lot of people think the car will actually drive itself. So they kind of sit back, or they sit in the back seat, or they go for a nap or something in the car with fatal consequences, and there's a lot of investigations nowadays into these so-called Tesla accidents, particularly in the US. But the whole idea of the level of autonomy in those cars is that they will have some sort of automated functions, but there's always meant to be a standby driver ready at every instance to take over. And that's the thing that people miss. The other thing that's driving the big increase in software content in the car is the whole climate protection thing, which is a huge issue nowadays, as we know, like with all the recent news around COP26 and so on. We're trying to cut down emissions from cars, and we're also trying to make the cars more fuel efficient as well. So, and tied in with that is the whole sort of electrification of the powertrain. So moving to EVs is all more and more and more and more software all the time. Because, if you think about EVs, electric cars, you take away the combustion engine and you've got the car driven by electric motors. And electric motors need very, very fine control algorithms to get the maximum performance from them. And the way you do that is with very sophisticated software. So all these new features mean more and more software, means more and more demand for people that understand this software and are able to write and develop this software.
So if I could just repeat something back to you, and then you can either kind of confirm or correct or whatever it is. So really what's kind of driving this is moving away from a car or a vehicle being a mechanical object to more of an electronic object.
Exactly.
You're nodding, so yeah.
That's a good way of putting it. Yeah, it's more what they call mechatronics. There's a term mechatronics, which means a mechanical device with some integrated electronics or software to control it. So if you think about a valve, for example, you can have a manual valve like a tap on your sink. So you manually control it. But imagine, say, you have a similar valve, which a lot of people will have now in their central heating systems, where you've got a sort of electronic control that opens and closes the valve at a particular time of the day, for example, and it regulates the amount of water going through the system. So imagine you've got a little piece of software and you've got a little electronic gadget that turns that valve. That would be an example of a mechatronic system. So there's lots of little examples of that in the car. Say your air conditioning, climate control system in the car, all the little flaps that will, when you turn the button and you want the air coming out at your face, or you wanted to direct it up to the windscreen on a kind of cold, wet winter's morning, you're trying to defrost the window. The little flaps inside the system that direct the air up to your windscreen are actually controlled by little stepper motors. So that would be another example of a mechatronic system.
I like that term mechatronics. It kind of sounds a bit sci-fi, but it does make a lot of sense, and I can see where you're coming from with that. And I suppose the reason perhaps why automotive computing is perhaps treated as a sub-discipline is, I suppose, the stakes involved in that. You're talking about valves on a tap or a heating system. If one of those goes wrong, it's probably not the end of the world, okay? Whereas if something in a car system, like the braking system, if the computer systems, fail, well, there could be a fatality.
Yeah,
so the stakes are quite high.
You're actually absolutely spot on there, Rob. Like one of the distinguishing features about this whole area, I mean, the general term for the whole area that we teach is called embedded systems. And embedded systems is essentially where you've got a microcontroller. So think of a tiny little computer. Imagine something like, say, a little computer with the power of an iPhone or something, or a Raspberry Pi. Imagine a little gadget like that sitting inside some process controlling it. Could be your washing machine would have one, your microwave oven would have one, your TV would have one, your smartwatch would have one, and so on. So all these things are little computing devices, but when you actually use them, you don't think about it as a computing device. You don't think about your washing machine as a computing device, or your microwave, even though there is a computer controlling everything inside it. You just think about the function of it. So the term embedded means that it's embedded in a process, that you're sort of unaware the computer's there. It's kind of in a background role, but it's managing everything in the background. You're not sort of consciously aware of it, that you're interacting with a computer when you turn on your microwave. But that's what you're doing, really, And it's the same in the car. There's loads of these little what we call electronic control units inside the car, ECUs. So you'll have one in your climate control system, you'll have one in your steering system, you'll have one in your gearbox, you'll have one in your engine, you'll have one in your sunroof, you'll have ones in your doors. If you have these little fold-out electric mirrors on the side of your car, you'll have one on each side, and there's on a high end car, like say a high end Merc or a BMW, there will be maybe up to 70 different controllers. 70 of these little computers. Imagine 70 iPhones inside your car, and they're all networked together as well on maybe 5 or 6 different types of networking technology. So they're all like a little internet inside your car, and they're all sending messages to each other saying, he's in now, the door is closed, he's turned on the ignition, I can start up now, and I can turn on the radio, and I can play his favorite song, and I can adjust the seat. The seat might have maybe 20 different motors in it, so I can adjust the seat to Brendan's position or Dave's position or Rob's position, because it'll know who's in the car and all this kind of stuff. So it's fascinating what can be done nowadays, just with bits of software and bits of electronics, all communicating inside the car.
So David, you're talking to us. You're in Cambridge in the UK today when we were speaking, correct? Yeah.
Yeah, that's correct.
So David, like, what is your job title now, and where are you working?
So where I'm working now is a company called Aplas Ideata. It's predominantly just an engineering consultancy and service supplier to the automotive industry. So effectively, any of the major vehicle manufacturers, if you look at any car just down the road today, chances are we do work for them. So I'm kind of involved in a number of different projects with those different manufacturers. And what I do is a lot of kind of functional safety work and a lot of connected vehicle R&D projects. So it's quite varied in the role. You're not stuck doing the exact same thing. One particular part of the car, let's say, you get to work on many different parts of the vehicle, which is always quite nice from a experience point of view.
So when you're saying, the car that you might see in the road, like you're not talking, I mean, Brendan's talking a high-end Merc. I mean, you might do work with Mercedes, I don't know, but equally, if somebody has a kind of a Commodore Garden Ford or something from the Volkswagen group, the cars that I will say regular people who aren't fancy like Brendan have. You're talking about the systems and the parts and these ECCs, was it? Sorry, ECUs that are associated with the various parts. You're working on those and you're developing better versions of that. Is that correct?
Yeah, that's the case. I think Brendan kind of gave an example of somewhere between 50 and 80 ECUs in a vehicle. A lot of people work on just one of these ECUs, and not only that, they all have to kind of work together. So in most cases, you see a vehicle on the road today, it's not just the vehicle manufacturer who has made that car. It's a massive team behind the vehicle manufacturer, what you kind of refer to as maybe tier 1 or tier 2 suppliers also working in the development of those cars. So like sometimes I go down to London, you might see quite a high-end car from, let's call it a premium UK manufacturer. And, there, as Brendan mentioned, there's like internal networks in these vehicles. I have quite a good understanding of how exactly that works. And because I've gotten to worked on one small piece of software inside that particular car. And it's quite nice being able to see that kind of on the road and thinking, yeah, you've done some work on that.
Okay, so could you maybe talk us through a kind of an example project or something that you might have worked on? Maybe, obviously not looking for any trade secrets now or anything that's sensitive, but is there any kind of an example of, look, there's a car that's driving around now that you might have seen, and I did this particular part on it, or I was involved in that, and this is how it works? Yeah,
and so there was one particular project I was involved in for a UK vehicle manufacturer, and admittedly it wasn't anything special. It was kind of a climate control ECU for this particular car. It didn't do anything fancy, but effectively it was routing a lot of messages from one network to another. So in addition to actually doing the climate control for the vehicle, there was a lot of routing of messages between the different networks in the vehicle. So again, a lot of kind of software development. So embedded C, as kind of Brendan mentioned, some of that I got to do during my time in applied computing at WIT, and kind of carrying that forward into my own work. And even things like playing with things like Arduinos, which I used to do back in the days, and still do today. You get to carry that kind of experience into work, and you're effectively working on a automotive type Arduino, if that makes sense. But it's those skills you kind of carry forward, and get to do interesting stuff with.
So when we're talking about automotive computing and automation, which is the stream, but it's the general kind of sub-discipline, you're talking about computing impacting on real world things. And I suppose there's a lot of crossover with the Internet of Things, as we would talk about. But why it is a separate thing is because of the stakes. With, these are lethal weapons if they, in the wrong hands. And I don't mean that in a flippant way. Okay, I just realised what I said there.
But there is a kind of a convergence between the two, as you say. The Internet of Things, we share some of our modules on the course with the Internet of Things stream. So some of our automotive modules, in particularly in fourth year, we share them across the IoT as well. So people that are doing Internet of Things will get the option to do some automotive modules. It's a nice blend, because what's happening, you started off the interview by mentioning infotainment systems in cars. And there's lots of connectivity now from the outside world into the car, which brings up cybersecurity issues as well. Another big area for software developers inside the car. So there is a convergence between kind of like mainstream IT technologies. Like there's Ethernet now in the car, so it's kind of customized to be more robust for automotive, but it's still the typical TCP/IP stack that's used in your internet at home, and on the web and so on. But there is this kind of convergence now where the car is being connected back into the cloud using various cellular technologies, as well as kind of like a Wi-Fi type technology called Car2X. The new Volkswagen Golf already has this, so it can kind of get information from other VW Golfs and things that it might pass on the road. They can exchange information with each other. So maybe if, for example, a Golf further up the road slams on its brakes because it comes across an accident, cars further back on the road can get the same information and be prepared then. So it's kind of like giving the car an extra set of eyes, so it can kind of see things that the driver can't visibly see. Like normally if you're driving along, you can see the road just ahead of your car, but you can't see what's going on 2 or 3 or 10 cars up ahead of you. Whereas all this new technology is allowing you to do that because of this connectivity. So there is a kind of a convergence now between the embedded world and the sort of mainstream IT world. There's a bit of crossover there. So what we're doing in the automotive and automation stream is we're giving people the skills to kind of go from the sort of IT world that they would be doing in their kind of common modules, like, programming and Java and cloud and network, to take those and to be able to interface into the low-level stuff that's happening in the car. So you said that, things can go wrong with a car. So, you don't want to have a dangerous situation because some of the software in the car is incorrectly programmed or doesn't work or some fault happens. So there's a lot of safety processes, like Dave mentioned there, the functional safety. It's a big issue, and we teach students how to do that. We actually just this week, just yesterday, in fact, we had some people in from one of our partner companies, German company, who is big in the whole tools and technology and functional safety thing. But we actually did a functional safety workshop with our fourth year students, where the people from industry kind of walked them through an actual example using a tire pressure monitoring system in a car. And we went through kind of a what if analysis, like what if the tire pressure monitoring system said your tire pressure was low, but it wasn't actually, or vice versa, So there's kind of like a fault that could manifest itself. And we looked at all the different scenarios and analyzed those and tried to put in place kind of mitigating factors that would alleviate those problems. So it was really, really interesting to get an industry perspective on that.
I'd just like to get a clarification on something that you said there a minute ago. You mentioned when you're working with low-level stuff. And I suppose I know what the answer to this is, but I'm kind of putting it to you in case somebody's listening thinking, oh, low level means low stakes. When we're talking about low level, it really means kind of closer to the metal. It means closer to the hardware as opposed to high level, which is a more abstract software thing. It's nothing to do with the value judgment. Yeah.
No, exactly. Yeah, it's basically. I mean, people often say, we're dealing with firmware. It's kind of like where software meets hardware. There's an interface between the two. So one of the skills that is important in embedded systems and automotive is this kind of understanding of how the software controls the hardware. It's not something that's really relevant if you're working way up what we call the stack. So you're working way up at the cloud level or maybe developing websites or databases. Typically there you're sitting on a big layer of software that you might buy from Amazon or Microsoft or somebody. And they do all the kind of low level detailed work for you. And you're kind of building on top of them. So you're kind of sitting on their shoulders, if you like, and you're reusing a lot of their work. But with embedded, you're actually down there and you've got nothing underneath you but the hardware, the actual microcontroller, and you've got to start building things right from the ground up. So it's kind of like building a house brick by brick instead of buying ready-built walls that you could just slap together, You've got to build every single component up. And you've got to make sure they fit together and that they work and that, and you've got to do crazy things like make sure that your CPU, your microprocessor is powerful enough to be able to deal with anything that's thrown at it in a typical driving cycle. So somebody's driving their car, lots of different events are going on. They're getting in the car, they're opening windows, they're closing windows, they're turning all the knobs and dials on the dashboard, and the engine is doing lots of different things, like thousands of times a second. And these little computers I mentioned earlier, they've got to react to all these different events coming in. And if something goes wrong on your PC or on your iPhone, and things get a little bit sluggish, and you kind of put up with it for a little while. And I always give the example to people: if you if you type in a URL into a web browser, say you type in www.wit.ie, and you expect to press the button and the site to pop up straight away. And if it doesn't pop up straight away, but it takes 2 seconds, that's okay. If it takes 5 seconds, that's still okay. If it takes 10 seconds, you start kind of twiddling your thumbs, and if it takes 20 seconds, you're probably gone. You won't wait. But so you'll still wait quite a while. But because the value of the thing kind of gets a little bit, depreciated. You're a little bit kind of annoyed the longer it takes, and your kind of satisfaction rating, if you like, is dropping off as you're sitting there waiting. But with embedded systems, there is a kind of a cutoff point where you basically drop off a cliff. So if the thing doesn't come back to you in like milliseconds, so the thing doesn't react in, say, 10 milliseconds, it's no use if it reacts in 11 milliseconds. So, if you think about something like an airbag, if a crash sensor on a car detects a collision, you want that airbag to go off within 20 or 50 milliseconds. So there's a kind of a hard deadline on that. And if it doesn't obey that deadline, there can be, fatal consequences. So you've got to make sure that the system, your microcontroller, your little computer in the car, can react under all circumstances within that very, very tight deadline. And that's the tricky bit,
David, you're nodding away there. Obviously, this all kind of makes sense to you. So you graduated in 2012, you said, wasn't it?
Yeah.
Okay.
Yeah.
Okay. So 2012, and you've been in the UK working in this industry since. Yeah?
Yeah.
So I mean, you're still there now. So I'm assuming you like it. I'm assuming like you could move and do something else if you wished, but you actually like this, do you?
Yeah. It's definitely quite interesting work. It's like I think what I quite enjoy most is that you kind of never know what you'll be doing in 6 months' time. Something new and interesting could come along, and Brendan was kind of talking there about some of the interesting problems about things like airbags, and I'm having exactly some of those challenges, just with different parts of the car, some of which are ridiculous requests from the vehicle manufacturers, and some of it is just more style over substance. So they want to make something very aesthetically pleasing, but as a result of that, they have to do significantly more work and analysis, software, hardware, to actually, make this particular thing, look nice. And it's just like, okay, cool, but it's a lot more work just to, so it just this thing looks very nice.
So, like, David, would you have always been into cars?
I actually don't like driving at all. I
I think that's brilliant. I love that. I think that's great. Yeah. Wow.
Yeah. I learned to drive about 4 years ago, I think.
Okay.
So would have been here about 5 or 6 years since, and then I learned to drive. I still don't like driving, but it's yeah.
Okay, so then to kind of back that up, then, if you're not into cars, what you're kind of saying is that you don't have to be a kind of a gearhead to be, and no. I know nothing about cars, by the way, to be into this kind of stuff.
No, absolutely not. I think, as Brendan said, you interact with some system, whether it's a washing machine, a fancy fridge, a smart kettle, take your pick. At the end of the day, it is, a small microcontroller, something like an Arduino, with some software, a little bit of hardware, doing something fun and interesting. And typically, if there's an LED on it that flashes, that's, those are the things we like.
Yeah. So David, could you give us a kind of an example of maybe a project that you might have done at college that has kind of informed what you're doing now, or you really kind of, really brought things together for you?
Yeah, I think when I used to go to, I think, what was the forum back in the day, I went to one of the little kind of nights there where you dress up as a movie character, what have you. I think the movie Iron Man just came out. What I had was I think it was like the little arc reactor from Tony Stark, and I had just got that hooked up to a very small Arduino, and it was just running a PWM, or a pulse modulation, making it glow. I think I went into the pound shop and bought a disposable camera, and likewise had 2 contactors on my hand with a light. So I embedded the actual flash from the camera inside a little LED light thing. So when I pressed my finger and thumb together, I mean, I had like a transistor here, and running some power into the flash just to get the effect. But I had like a 9-volt battery embedded in my jacket, and I was kind of thinking, a little bit dangerous, but it was effectively bit of software doing, making it glow, so you have a little timer, increasing the pulse modulation, coming back down, and those are just the types of things I liked making things, and if you can control it by software, even better. It delivered the effect, and I didn't burn myself or electrocute myself yet.
I this is gas. You're giving me flashbacks now, because I remember that. Because if I'm correct, now, first off, you've invoked the forum and an indie disco on a tech podcast, which is like props to you. But I was DJing there that night, wasn't I?
You probably were, yeah.
I think I was, yeah. And I think I remember you coming. I'm remembering that costume now. I remember seeing you there that night.
The full circle has been closed now, yeah.
That is gas. That is brilliant, absolutely gas. But I like the way you're thinking. I can see where you're coming from with that. Yeah. So what the kind of the gist of it is that these skills and these kind of technologies, they're not they're applied to the automotive industry and to cars and vehicles, but they're not unique to that. So, I'm sure those skills and those technologies are used elsewhere as well.
Definitely.
Yeah, medical devices is another good one. I mean, there's a lot of medical devices companies in Ireland, and some of our graduates, actually, there's a couple of graduates. I can think of 2 people in particular who started out with us early on when we've been teaching this automotive software stuff in WIT for 20 years now. And some of the graduates at the time who went out into the industry and spent many years working for some of the major car manufacturers in the UK, and have come back to Ireland, and they're working now in some of these medical devices companies. So the skills are very transferable across lots of different industries, like factory automation. Think about any of the pharmaceutical companies in Ireland, any of the kind of chemical manufacturing companies. Energy management is a huge thing now. You think about all the gadgets people are using to kind of reduce the energy consumption in their houses, smart devices. I think if you're a geek at all, you'll love this kind of course, because you get to play with all the technologies. We're applying it to automotive, as a kind of an area, but you don't have to go and then get a job in automotive. Like, you can then take those skills and you can go and work for any of those embedded systems companies. You could go work for Dyson, creating the next fancy vacuum system, or there's no end to the opportunities that are out there. And the automotive industry is just a very interesting area at the moment, particularly with, say, you think about autonomous vehicles that are becoming more and more talked about, and more researched and developed. You think that Apple, the Apple who makes the iPhone, they're spending like billions now trying to make an autonomous vehicle, and this project has been going for many years with them. Dyson set up an autonomous vehicle research development center. They spent a couple of years working on it. They realized that the problem was so ginormous. Like, they've got huge expertise in motors. Like, think about all the products they have. They're all basically motors, aren't they? All the Dyson products. So they've got huge expertise in motors. And they thought, okay, let's take that motor expertise and let's build an autonomous vehicle, because it's only motors really, and we just control the motors and they drive around. But when they started that, they kind of underestimated the magnitude of the problem. And they spent billions on it. Dyson spent billions of his personal fortune on this. And then I think after about 5 years, he closed it all up. He said, I realized that, this isn't going to be economically viable, because it's going to take us like so long to get there. And I know some of the people who work there, and unfortunately they got laid off, and some of them ended up going to places like McLaren, who are adding electric vehicle technology to their supercars and things. So the skills are really transferable. But one of the problems with companies like Dyson and Tesla to an extent, but they're kind of on a different track. But Apple is, because they understand all the software, they understand all the the microcontrollers and the typical IT kind of stuff, but they've got no expertise in the process of building a car. Like making sure that when they physically build a car, all the panels match up. This is a problem that Tesla has, that, they build a car and there's huge gaps between the door and the frame of the car. And, things don't quite fit and things fall off. And, all the software is state of the art, you can get your automatic updates over the air. But bits will fall off the car because they don't know how to build a car.
I have read a couple of weird things about Tesla and strange kind of quality issues for cars that cost in excess of $100,000.
Yeah.
It's not like you're buying a cheap budget model, shall we say?
No.
It's kind of mad.
But there's huge issues, and so when you get to look at things like embedded software, it's the safety, and it's the kind of attention to detail, really, and the processes, the process of developing the software, and a huge area as well is more and more of the software and the systems are being simulated. So they simulate the microcontrollers themselves are virtual. So same way we have maybe the concept of virtual machines is quite common nowadays. So a lot of students would run Linux, Ubuntu or something on their Windows laptop, so that they can run their Unix, Linux programs on their Windows machine, or They might have an Apple Mac that they can run Windows on. They can dual boot and use virtual machines. In the automotive industry, a lot of the actual microprocessors are implemented as virtual machines on kind of supercomputers, so that all of the vehicle software can be run in a kind of a simulated virtual environment before the actual hardware is ready, because the development cycles are becoming much, much shorter. They've been reduced from about 5 years development for a new car down to about 2 years or so now. And that's kind of squeezing everything to be more productive. And it means, and think about, at the same time, the amount of software in a car is going up exponentially, but the development time is going down. So something has to give. You need more programmers, you need more software developers with the skills. So the industry is crying out at the moment for people with these skills. And we find that anybody who wants a job in the industry after coming out of our course can just walk straight into a job. Because one of the things we've always done from day one when we started doing this is we always said, we're going to use industry standard tools on our courses. So we're going to train our students to use the tools that they use in the industry. We're not going to use kind of, open source academic tools and kind of made up little simulations and things. We're actually going to use the industry standard tools. And we've been lucky enough to kind of partner with a German company who's the leader in these tools, and all the car manufacturers, you name any car manufacturers, they're a customer of this company. And they use their tools. So we've got a good relationship with them for the last about 20 years. And we've got a fully equipped automotive lab in WIT, full of their equipment, their hardware, their software. All the students doing our modules get free copies of their software, which, a single copy to industry is about 30,000 euros. Our students get a free license for that on their own PC, so they can use it at home. They can use it with the equipment in our lab, so they can build networks like the ones in the cars. They can debug it. We've got equipment in the lab like things like instrument clusters. We've got climate control units so that we can play around with these things, and we can kind of build bits of a car, the electronic systems in a car. And as well as that, the engineers from the company, they come over a couple of times a year and they give workshops to the students like they did yesterday. And they train the students how to use the tools. So they're getting valuable training from this company. So when they leave, they can literally walk into any company and they can hit the ground running because they know the tools that these companies are using. And it's brilliant, Same way, we've got companies now setting up in Ireland that are using these tools. We've got Jaguar Land Rover, who set up a huge software development center over in Shannon. They're employing, the last count was 500 people, but they're growing exponentially over there. They're developing autonomous vehicle software, all the stuff we've been talking about today here. And we have some of our undergraduates are going to do work placement there. There's 3 of our graduates going to do work placement there next year. There's 2 of our graduates already working there for the last 2 years. So there's a kind of a nice ecosystem now, automotive ecosystem building up in Ireland. There's even a new, David is talking about the connected autonomous vehicle stuff that he's responsible for over in the UK. We now have a connected autonomous vehicle test bed, if you like, over in Shannon, just in the area around the airport. It's a company called the Future Mobility Campus Ireland, recently set up. They're only just getting going now, but it's a place where companies can go if they're developing autonomous vehicles or some of these cool features for driving assistance systems. And they've got a whole platform, they've got a whole area over there that they can test out all these in different environments. And they've got all the sensors wired up on the roads, and they've got the kind of smart traffic lights that they can sequence automatically from the car and all this kind of stuff. But all this is kind of a happening thing now in Ireland, which is fantastic for our graduates because, when we started doing this about 20 years ago, there was like 2 companies in Ireland that were involved in this area. So at the time, most of our graduates went to the UK, Germany, Asia, and the car companies there, and ended up working for all the big kind of names. But it's great to see all this kind of happening now in Ireland, so that we don't need to send people abroad to get this experience. You know? And we can always get people back as well, David, can't we?
Yeah.
So I'm just trying to think now to summarize where we're at. So you've discussed a lot of hardware. You've discussed a lot of kind of, when we say low level stuff, that's what we mean, kind of closer to hardware. But it's not electronic engineering. It's focusing on the software that controls the hardware, but at that low level. So, and the way you're describing it, like even like the automotive applications, but then that can be, you know, equally as applicable in the medical devices area or something like that. What you're talking about is kind of, I hate to say the word mission critical because it's probably not descriptive, but you're talking about systems where there are stakes. So if I build an app on the phone that checks football results, and as you said, Brendan, if it takes 10 seconds to bring back the football results, it's not the end of the world. But if it's 10 seconds reporting a heart rate variation on an imager, that could be the end of the world, you know. Or an anti-lock braking system that doesn't kick in until after the fact, way after the fact. That is the end of the world. So you're talking about somebody who's really somebody who is into software, has a level of detail, and is maybe interested in those kind of applications. Would you say that'd be fair?
Yeah, that would be a good summary of it. You mentioned that we're not kind of electronic engineering. We're kind of at the interface, as we said, between hardware and software. But we do teach the students enough of the basic electronics so that they are able to interface sensors and things to the microcontroller. So, you know, if you want to do something like measure temperature, or, you know, you want to connect a disposable camera flash bulb into your clothing or something, you know enough electronics to be able to do that. So it's not the kind of same skill set as somebody doing a 4-year electronic engineering course. You wouldn't have that depth of involvement with the hardware because, you know, on an automotive project, the hardware will be somebody else's responsibility. If things go wrong, you need to know whose fault it is, basically, you know. Is it a hardware issue or is it a software issue? So you need a minimal understanding of the area.
David, what would you say are the key skills that a student or a prospective student might need to get into this area?
I think it's just having a particular interest in software development. So for me, coming into WIT, I didn't have much. I had a little bit of experience with C and a little bit of experience with Java. That's just for me doing my own, you know, little projects at home. I think coming into just having a general interest in those types of topics, I think are quite good. I think it was something, I can't remember who said it, a previous lecture, but it was something like software engineers are kind of a dime a dozen, but the kind of difference is, you know, how well you make software. You know, anyone can write software, but not everyone can write good software. And I think that kind of resonates a bit with, you know, the difference between doing something in 10 milliseconds and slipping into 11 milliseconds. So I think just anyone, if I was to be recommending kind of reading, I think having, you know, playing with things like an Arduino, Raspberry Pi, having an appreciation for things like Python or just embedded C or C++, I think definitely goes a long way. And those skills are actually, in my opinion, quite transferable. So you mentioned automotive, definitely things like healthcare, robotics, you know, all those are very much used in those fields.
Excellent. Brendan, if somebody wanted to find out more about the automotive group, have you got a website for the research group?
Yeah, we have. It's just simply wit.ie/automotive.
Okay, very easy to remember.
So
you've got loads of information up there, and I'm sure if anyone had any questions, they could contact you, and they can look you up, Brendan Jackman, on the WIT website. David, thank you so much for talking to us today, and I don't know, I'm going to say, if any students had any questions, would it be okay to forward them on to you?
Yeah, no problem. Happy to help out.
Lovely stuff. Well, listen, lads, thanks so much for speaking to me today. The automotive and automation, it's been a learning experience for me. I've learned something about it that I didn't know before. So that's what I like doing about these podcasts. I always learn something.
Me too.
And thanks for jogging my memory of about a fancy dress party in an indie disco in Waterford back in the Beyonds. Wow, fair play to you, dude.
Thank you.
Listen, lads, thanks so much. Thanks for chatting today. If you liked what you heard, leave us a review. Machine_podcast on Twitter, blah, blah, blah. Right, thanks. Cheers, lads.
Thanks, Rob. Thank you, Rob.
Thank you.